and then we can go on to the actual course. So first, I'm guessing these times are okay for everyone, right? Because we tried to set it up so there would be no clash. Yeah. Okay. The second thing is that so we'll have these lectures, and the idea is that we have two potential TAs, Manish and Atharv, whom you might know. So it'll be helpful actually if if all how many, if you have a sense of how many of you are going to register for the course, because that determines how many TAs we can have. So it'll be nice if you tell the academic office. That's also true, by the way, for the participants on Zoom. The participants on Zoom, if especially the ones from TIFA Hyderabad, and if some of you from TIFA Bombay are listening to this recording later, please try and register and tell our academic office, the ICTS academic office, that you're registering for the course, because that will help us just determine how many TAs we have. Okay, good. So that's one thing. The second thing is that we'll maybe one of you can do a whoever is the TA or both of your TAs a tutorial once a week. So the idea is we'll try and have some assignments, and even if there isn't an assignment, maybe you can do a tutorial which you can schedule with them whenever you like. So maybe like 1 hour a week apart from the lectures. Okay, good. The other thing is we'll try and have a number of assignments. So we'll try and have, if not an assignment every week, at least some significant number of assignments. And most of your grade will be based on the assignments. Sometimes I think for them we did 75 and 25%. We could do it otherwise also. But one thing you should kind of keep in mind is that, so just actually this is an important point, is that, your grade in this course really doesn't matter. Okay, so we are not, please, like, that's not something that's important. And in particular, when you look at the assignments, you should know that the assignments will very largely be very similar to the assignments they received in the previous year. Not the exams, but the assignments will be. So in principle, if you really just wanted to do your, and you're allowed to collaborate on your assignments, you're allowed to discuss on your assignments, okay? Not in the exam, but you're allowed to discuss on your assignments. Just when you submit your assignment, just write who you discussed with, yeah? But of course, you should all write your assignments on your own, but you can discuss the solutions. So the assignments are not meant as a test, okay? It's not a weekly test where you're being tested every week on your knowledge. It's something to help you learn, okay? And it's important that you take that seriously from your side. If you just want to find the answers, you can find the answers of many of these things and copy them down. But the objective is to help you learn. And it's not really an assessment exercise. And we are not really interested actually in this course in trying to make some very accurate exam type assessment. Okay, the important thing is that you should learn the subject. That's why I want to say, the assignments are similar to the ones last year. So you could kind of go to your seniors and ask them for solutions, but I hope you won't do that because there's, it'll just prevent you from learning. Okay, good. So that's about the logistics. Are there any questions about that? You should switch on this AC or open the windows. Maybe I'll open this actually. This we can open this, right? Does it make? Maybe it spoils the recording. I'm just wondering if if it spoils the recording, the noise. Okay, are there any questions about the logistical parts? Okay, good. Sounds good. Okay, how many of you have done QFT before in some form? Many of you. Okay. Okay, so this is an introductory QFT course. So those of you who haven't, you don't have to be worried. We'll kind of start from the beginning. And hopefully that will also be useful for those of you who are doing QFT for the second time. We'll try and go on to some more advanced topics, although that depends on how fast we make progress. Also, one more thing is we are going to miss a few lectures. We'll miss one lecture in February. We'll miss 3 lectures actually because I'll be traveling, and then again in April we'll miss perhaps for 2 weeks lectures. So we'll do some makeup lectures at some point. Yeah. Okay. Okay, good. So are there any questions or? Okay, please try and speak up in this class. If you just stay silent, I don't know if I'm communicating effectively or not. So you should really try and speak up. Okay, one more exercise. So I'm Suvrat, as you know. I'm going to do one exercise of asking all of you for your names. I'll probably not remember, but I'll try again and then I'll remember. Yeah. So maybe we can just go around and do one round of introductions. Maybe we'll start with. Okay, great. Okay. Yeah, okay. I know you. Yeah, both of you know. Okay, okay, sounds good. So I might forget, but I'll ask you again. Yeah. Okay, good. So just feel free to ask questions. As we go along. That's also true for the Zoom audience. As I said, once again, it'll be useful if you show yourself, but it's not strictly compulsory. But feel free to ask questions. I think you should be able to speak on this. Yeah. Okay. So I want to start with some very general things today and talk about why field theory is necessary. But before that, I just want to give you a sense of where field theory fits in, at least the way I think about how modern physics works. Okay, so the way I think about things is that there's one very important branch of physics which we call mundane physics. But mundane doesn't mean boring, which is just everyday physics. Okay, if you kind of throw this piece of chalk and you want to ask how high does it go, and we know how to calculate that. We know the basic rules that govern that. We've known the basic rules for like 300 years. And there are Newton's laws and there's classical physics, which tells us how to work that out. Now, this is something which is still very important. It's very important because not only is it does it govern much more than the chalk, it's also what governs the space missions of ISRO are all basically governed by this kind of physics. And if you look at other systems, fluids, life, physics of life, and so on, we ourselves, we are all basically governed by this kind of physics. Okay, so this is very important. But about now more than 100 years ago, we realized that things start happening when you look at large relative velocities. Okay. And when you do that, you get special relativity. And what's different in special relativity from mundane physics is that our notions of space and time change. Okay, so our notions of space-time change, and that's why it's not mundane. Okay? That's why in some ways, special relativity is counterintuitive, because it tells us that we need to look at space-time in a new way, in a different way, not the way we are used to. Right? And this all of you have studied and know well. Right? Now, it turns out that if you look at strong gravitational fields, then you find that there's something you get which is general relativity. And general relativity, also is basically changing our notions of space-time. Okay. So it tells, this is the modern theory of gravity, and this is very important for how we understand the universe and so on. But conceptually, general relativity, it's giving us new dynamical equations telling us how to think of gravity dynamically. But what it's still doing is still working with the notions of space-time that special relativity taught us to change. Okay. Now it turns out that if you look at, it turns out that if we started looking at atomic scales, people discovered, then we came to something else, which was quantum mechanics. And quantum mechanics is, also changes something from the way we think of our mundane notions of space-time and mundane notions of physics. And what it changes is something more dramatic, right? What it changes is our notions of reality. So it tells us that, so in special relativity, what was changing was in relativity, we thought two events were simultaneous, but we realized that, if those two events are not happening at the same spatial point, then simultaneity is something that depends on the observer. And that's surprising. But in the case of quantum mechanics, something even more funny happens, which is, we are generally used to saying that, there's some definite, definite state you can assign to objects. Definite state where we think of a definite classical state. We say the chalk is here, then it's not moving. And as we know, that doesn't work. And you can have, our notion of how you describe reality now changes, and you have to describe reality in terms of a wave function for a state, which assigns a set of amplitudes for different kinds of classical states. So our notions of reality change, and that in some sense is very radical compared to even what special relativity did. Okay? And then you can start. So this is something we understand well. We understood now for many years. And then you can start asking what happens if you put together some of these regimes. Okay. Now, there's something important which I want to emphasize, which is that quantum mechanics was really a radical break from mundane physics. Right? It's just very different. It's not that it's some kind of form of physics, of normal physics, where you can apply Newton's laws and kind of make sense. It just our notions of mundane physics just don't work. Right? Special relativity is a little less of a radical break, but it is still a break from the way we understand mundane physics. Right? And so you really need to change some, the formalism or the language with which you do things. Now, what we are going to discuss in this course is what happens when you start putting together some of these regimes. And in particular, the regime that we want to discuss is the regime where you put together special relativity and QFT and quantum mechanics. And that is the regime of QFT. Okay? And that is quantum mechanics plus special relativity. Okay? Now, one thing I want to emphasize, when you compare this to quantum mechanics and relativity, is that QFT doesn't involve, in fact, a radical break from anything that we did previously. Okay? And if you look at, for instance, the history that Weinberg gives in the textbook that Weinberg has, then you will see that, he points out how a lot of quantum field theory, which was stuck in its development for some time, started making progress after the Second World War. And some of the older people, older physicists who had developed quantum mechanics, sometimes wanted to change everything, because they were kind of born in revolution, so they wanted to, change the formalism of quantum mechanics. But in fact, it turned out that the people who made progress were the people who were more conservative, people like Feynman and Schroeder, who in fact were rather conservative. And they said, oh, look, we understand the principles of quantum mechanics well, we understand special relativity well, and we just have to learn to put it together in the right way. And so quantum field theory, in principle, is not something that's different from what you already learned in quantum mechanics. It's just quantum mechanics of an infinite number of degrees of freedom, and where the dynamics is consistent with special relativity. Okay? You can of course ask, what happens if you try to put this regime together? And this is the question of quantum gravity. And this we will not discuss in this class. Okay? This we will have nothing to say about in this class, although it's something that many of us here do research on. Okay? So that we don't completely understand yet, and might involve many new phenomena, but we will not have anything to say about this in this class. Okay, so we are not saying anything about this. We're only going to talk about quantum field theory. Okay, so that's at least how I envision how quantum field theory fits into the framework of how we understand physics. Are there any questions about this, or? I realize there's something I think was written in the course description, but which I didn't emphasize, which I remember when I was saying this, I'll say various things in the class, and you can take down notes, of course. The other the references to use for this are the lecture notes by Coleman, which we'll look at, the textbooks by Peskin and Schroeder, and the textbooks by Weinberg. Okay? So those are useful things, and I think that was written in the course description, right? So you already know that. Okay. Okay, are there any questions about this broad overarching framework? Okay. No questions. All of you agree with this perspective, or what about? Plus general relativity. Yeah. So yeah, you're right. So sometimes people do quantum field theory in curved spacetime, okay, where you try and treat relativity. You try and take some background spacetime, which is influenced by general relativity, and then you do quantum field theory on top of that. In fact, we might do a little bit of that now. There isn't something which is conceptually very new in that. There's some things one needs to learn, and we might even at the end of this course talk a little bit about it. But there isn't, and indeed, it gave rise to some interesting results about black holes and Hawking radiation and so on, just applying that correctly. But that isn't, at least here, I wouldn't put it as a big new box. It's not something that's conceptually very new. It's kind of even more conservative than what I was saying about quantum field theory. You really understand quantum field theory, and you just kind of, look at a different kind of quantum field theory where the background spacetime is not flat. Okay. 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 Let me just say something about units. So we'll work in units where h bar is equal to C is equal to 1, because, as I said, quantum field theory involves quantum mechanics and special relativity. And there are two physical constants that are important. The physical constant in the case of quantum mechanics is h bar. Right? And when an action becomes becomes comparable to h bar, where some angular momentum becomes comparable to h bar, that's where we know that quantum effects are important. But we are going to set h bar equal to 1. Okay? And similarly, we'll also set the speed of light equal to 1. Okay, so you will never, I think, in this course, except maybe once or twice, actually see these constants being restored. Okay? However, you can always restore them using dimensional analysis. Okay? Okay. As I told their batch also last year, sometimes I work in units where 2 is equal to 1. Okay, and that's a sign that you have to correct me. Okay, because sometimes we'll find that we'll work. I might not be that careful about factors, and so you should check whatever I write on the board. And it's best if you correct me in real time, but if not in real time, at least go back and check. Okay, good. So these are the units. We will talk about 4 vectors, which you should be familiar with. And I'm hoping all of you are familiar with this, right? With 4 vectors and how to use 4 vectors, so on. If you're not, maybe you can do a tutorial on it. And the sign convention I like to use, in fact, is that we have a metric. That metric looks like this. This is not always the sign convention that people use, especially in the relativity literature. People use the opposite sign convention, where the space indices go with a plus sign and the time index goes with a minus sign. But this is just how I learned the subject, and I'm happier with this. You're free to use the other sign convention, but this is the one we'll try and use in our lectures. Okay. What this means is that if you look at x nu, this looks like p squared minus x squared. Okay. Okay. And remember, as I said, the speed of light is 1. So there's no c we put here. Okay, good. Are there any other questions about this? Units and so on. Okay, fine. So now, as I said, quantum field theory is basically putting together quantum mechanics and special relativity. Right? But quantum field theory is quantum mechanics of fields. What's one key difference between fields and the kind of quantum mechanics that you study, in pre-QFT courses? It's true, particles are excitations of those fields, but that's true. That's true. Is there another key difference between fields? Okay, this is true. Yes, and so what does that mean? So in particular, yeah, more degrees. They have an infinite number of degrees of freedom, right? Which have an infinite number of degrees of freedom. So this is one of the key differences between quantum mechanics as you've done it and quantum field theory as we'll be discussing. Okay. Now, in fact, you can do quantum field theory in a way by regularizing the field. So, when people do quantum field theory on computers, they actually think of a lattice and they put 1 degree of freedom or some degrees of freedom at every lattice point. And then it's a lot like quantum mechanics, except that you still have a lot of degrees of freedom, right? And the physical effects that you get really appear in the limit where the number of degrees of freedom goes to infinity. So the fact that you have effectively an infinite number of degrees of freedom is one of the key aspects of quantum field theory. That's not the only thing. These infinite number of degrees of freedom have to interact with each other in a way that's consistent with special relativity. But one key difference is that you have an infinite number of degrees of freedom. Okay. Now, why do we need an infinite number of degrees of freedom when we have quantum mechanics and special relativity? Why can't we just say, we have some particles and they move relativistically, and that's it, right? When you learn special relativity, you don't immediately see that there's an infinite number of degrees of freedom. The way you learn it, often it's taught that there's a particle, and you can talk about the mass of the particle, the momentum, and talk about different events. But why do we suddenly need to introduce an infinite number of degrees of freedom when we talk about quantum mechanics with special relativity? Particles? Particle number is not fixed. Good. That's indeed one standard answer that's given, which is that particle number is not fixed. But in fact, there's something a little more crucial. And first, is there anything else? That's true. Particle number is not fixed. Okay, so maybe particle number is not fixed. Why do we still need to introduce an infinite number of degrees of freedom? Okay. Good. That's indeed one answer, and I will come to that answer as well. I want to emphasize another answer, but I want all of you to realize that this is actually a question you should think about. You know, when you do quantum field, huh? Is what? You see, but the good. You see, but the probabilistic number of quantum mechanics is also true for, when you have one particle. Okay, it's true that the number of particles is one reason why you need quantum field theory, and particle number is not conserved. In fact, I want to point out a more fundamental reason, which is not usually emphasized in QFT textbooks. Okay, why you need an infinite number of degrees of freedom, and this is something that's not usually emphasized. In fact, I don't know any textbook that actually discusses this, but I want to point out that the moment you think of dynamics with relativity, you're forced to have a number of forces. Okay. And this is an important point. So in fact, even if you were to do classical dynamics with relativity, you would still be forced to an infinite number of degrees of freedom. Okay. So it's not just the fact that particles can be created in quantum mechanics, which is of course true, but in fact, it's also the fact that any dynamics consistent with special relativity forces you to have an infinite number of degrees of freedom. Okay. You know why? Have some of you thought about why? Yes, okay, but why can't you just think of particles interacting with each other? Well, but haven't you seen a force at like some linear Dirichlet potentials in electrodynamics between two particles? It's true, it generates a field, but you can still talk of forces between particles. Okay, let me explain what the point is. You see, when you have particles interacting with each other, you've all studied electrodynamics, right? And have you all done the course? And you all studied the fields of moving point charge at some point. Okay, good. So you see, you can always talk about the force between two moving point charges. And if you try to solve the two-body problem in electrodynamics, you don't actually have to talk about the field. The field is an intermediate thing, and then at the other point you apply QE plus V cross B, you get the force on the other charge, and then you can solve the equations of motion. Okay? But there's something important when you do that, which is worth emphasizing. So let's say we have two particles, right? And I'll draw their world lines. And one particle is like this, it's doing something. And this is particle one. You understand what this means, right? This is the world line of the particle. So this is x as a function of t. So it's kind of sitting in the same place, but it's moving about a little bit, yeah? And here's particle two. Okay? Okay. Now, there's a very key point which is necessary when you have special relativity, which is the force on the particle 2, this F21, okay? The force on the particle 2 due to the particle 1, okay, cannot depend on the instantaneous position of particle 1. Okay? It cannot, because particle 2 cannot know instantaneously what particle 1 is doing. Rather, it has to depend on the retarded position of particle 1. What does the retarded position mean? It means that you draw the light ray back in time, and you see where it intersects this. So let's call this time, we've chosen some reference frame. Let's call this time t. Okay, and let's call this difference tau. the force on particle 2 due to particle 1 is some function, whether you like to talk, is some function, and actually it doesn't matter what the function is. It's some function of x1 at t minus tau and of its derivatives also, okay, x1 dot of t minus tau, and in fact of its second derivatives also if you go and look at this, okay. So it depends on the acceleration and so on of particle 1. Yeah? So the force on particle 2 due to particle 1 depends on what particle 1 was doing in the past. Okay? Similarly, the force on particle 1 due to particle 2 is some other g prime Okay, by the way, it also of course depends on what x2 is doing. So it also depends on x2, but x2 at time t. And you can also have sometimes x2 triple dot terms and so on. Okay, but that doesn't matter. The point is that this force depends on what x2 is doing at time t, okay, and it depends on what x1 was doing at a different time. Okay? Now, I wrote tau here, but in fact, this time, the retarded time here, might not be the same as this time. Okay? You see, if the two particles are just sitting at one place, then of course it's the case that the time lag, the time delay between this particle and this particle is the same as the time delay between this particle and this particle. But in general, the two particles might not be sitting in one place. So this time is a different time. This is some tau prime. Okay? And of course, it depends on x1 of t, x1 dot of t, double dot of t, and so on. Okay, is this clear? Okay. Now, how do we calculate this time tau? How do you calculate this time tau?
Excuse me, sir.
Yeah, is there a question? Yeah.
Why shouldn't it depend on the instantaneous time? Why on the retarded?
Why shouldn't it depend on the instantaneous time of particle 1?
Yes, sir.
Because that would be in contradiction with special relativity, right? The force on particle 2 due to particle 1, if particle 1 is not at the same point as particle 2, if particle 1 does something at this time, it takes at least time of light propagation for particle 2 to know about it, right? So one of the principles of relativity is that information can't travel faster than speed of light.
Right. Okay.
Okay, good. Yeah, sorry, someone is saying something. How do you calculate this tau? Yeah, exactly. But you see, to calculate this tau, you have to draw the light ray back and you have to calculate where it intersects the world line. Now, this tau is a dynamical function. This particle might happen to come very close to this particle at some point, in which case, tau might start going to 0, or it might start going far away, right? In which case, tau might start increasing, right? Do you see this? Okay. So tau is and tau and tau prime are dynamically determined. Okay, good. And to calculate tau and tau prime, and actually you will really see this if you ever try to solve the two-body retarded problem on the computer, you have to know the entire past history of particle 1 and the entire past history of particle 2. So to calculate them, we need the past history okay, and if there are n particles, we need all their past histories. Okay, so notice that you see usually when we do physics with these two particles, what is how many dimensional phase space do we talk about in non-relativistic physics? We talk about a 6-dimensional phase space, right? There's some degrees of freedom. There are 3 positions, 3 momenta, and part 6 and 6. Okay, there's a 12-dimensional phase space, right? So there are only 12 numbers. Just think of it on a computer, right? When you do non-relativistic physics, You keep track of 12 numbers. These are 12 real numbers, right? 12 numbers to track the dynamics. But when you do relativistic physics, you see it's not enough to keep track of 12 numbers or any finite number of numbers. Okay? To do relativistic physics, you need to keep track of functions. Okay, and these are infinite numbers. Because a function is a number at every instant of time. Okay? So even if you just do classical physics, forgetting about, and the reason you don't usually see this is because you very rarely, if you think about it, I doubt if any of you have actually done, a dynamical problem in relativity where you've really not just calculated the fields interacting with each other, but actually try to do a little bit more, where you have one particle which influences the other and which influences back the first one, okay, with relativistic dynamics. Okay, and that's something which is very hard to do. And you see, the moment you do it, you're forced to introduce an infinite number of degrees of freedom. In fact, these kinds of differential equations are different. So these kinds of differential equations are what are called retarded differential equations, or sometimes functional differential equations. Okay. So these are just fundamentally different from the kinds of differential equations that you're used to solving. And you see that dynamics of any set of particles, even if you have only 2 particles in the whole universe and you want to track their dynamics, you cannot do it by keeping track of a finite number of numbers. You have to have an infinite number of degrees of freedom. That's because you have to keep track of these past functions. Okay. So that is why any dynamics which is consistent with relativity, even if you're only talking about 2 particles and particle number is fixed, forces you to an infinite number of degrees of freedom. Okay, is this point clear? This is an important point. You should really understand this. Now, this is why fields force you to have an infinite number of degrees of freedom. Yeah.
So given an initial condition, initial distance and separation, can't I determine the world lines using the solution?
You can't. You see, let's say I give you an initial condition. So I told you, what do we say for initial conditions usually? We say, let me tell you what's happening at time t equal to 0. Right? Let's say I tell you the position and the momentum of both particles at time t equal to 0. Can you determine how they'll go forward? You have the interaction. What you mean the interaction? Remember, the interaction depends on the retarded time. So let's say, you see, usually when you might have even done this on a computer, I give you the position. I say particle 1 is here at this time. Particle 2 is here at this time. Particle 1 has some velocity and acceleration. Particle 2 has some velocity. That's what we usually mean initial conditions. Can you determine how they'll evolve forward? A free particle is just a straight line, correct. But we are not talking about free particle. We are talking about the 2 particles interacting with each other, correct. For free particle, it's a straight line and there's nothing to do. But the point is we have interactions, right? The thing is you can't, because you need to know not just what particle 1 is doing now, you need to know what particle 1 was doing in the past. Okay, so unless you know the whole past history of what particle 1 was doing, you can't actually determine, how it will interact, how it will influence particle 2. Okay, okay. So this is one way of doing relativistic physics, and relativistic physics, whatever way, even if you just think in terms of particles, forces you to introduce an infinite number of degrees of freedom. Okay, and this is an important point which you should really understand. Now, there's a slight problem with working with this system. In fact, this system is convenient to work with if you really classically wanted to solve number of degree, some of these 2-body problems. However, there's a slight problem with that, which is if you work with that set of equations, that's not good to make a passage to quantum mechanics. So at least nobody knows so far how to quantize that set of equations, how to quantize a set of functional differential equations. Okay, and that's because, remember, the way our passage from classical mechanics to quantum mechanics goes relies very strongly on this idea that we are given some initial surface and we have a Hamiltonian formalism. So the passage to Qn relies on having either a Hamiltonian or a Lagrangian formulation. Okay. Right? Okay. Now, what is the basic point of a Hamiltonian formalism? It is that there's a phase space. Okay. On that phase space, you're given some, you're given some degrees of freedom, and then you see how things evolve on that phase space. Okay. And there's some function in the phase space, which is the Hamiltonian, and you see how things evolve in that phase space. Okay. This is not quite of that form, okay, because in fact what we have is, the past histories. Okay. So it's true there's an infinite number of degrees of freedom, but it's not in the form that's convenient to put in a Hamiltonian formulation. Okay. So the way fields solve this problem is in a slightly different language. Okay. The way fields solve this problem of dynamics is by saying in a different way. What do fields do? What fields do is they say, well, rather than saying that particle 1 interacts with particle 2, we will introduce an intermediate field, which we'll call the electromagnetic field, and we will say particle 1 interacts with particle 2, interacts with the electromagnetic field, and the electromagnetic field interacts with particle 2. Okay. So we have 1 and we have EM field, and both of these interact with each other, and then this interacts with 2. So we introduce the field as an intermediary. Now something slightly different. Now what happens is that the field and the particles only influence each other completely locally. Okay. Remember that the force on particle 2 now looks like Q into E plus V cross D. But all at time t, this force at time t looks like Q of E of t plus V of t cross B of t, not at some retarded time. Okay. So the field at a given time influences the particle at that time. That's because we are talking about the field at the same position as the particle is. Okay. And the field somewhere else doesn't influence the particle. The particle at this point, is only influenced by the field at that point, not by the field somewhere else. Okay. And so that's consistent with relativity. But now we've paid a price. The price is, rather than talking about two particles, we now have these infinite number of degrees of freedom sitting in the electromagnetic field. Okay. The electromagnetic field you can think of as a way of keeping track of the past history of particles. Okay. If I gave you initial data for the particles and for the electromagnetic field, then I could compute what the past history was. What was, how did this electromagnetic field get produced? Okay. But, this way of doing things now just, gets rid of keeping track of the past history, but instead we keep track of this electromagnetic field, but now at every point in space. Okay. And keep track of it at every point in space. Yeah, you see, the point is whether same time or different time is the point. The particle only interacts with the field at the same position and time as it is at. The other particle also interacts with the field at the same position and time that it is at. For those two particles, there's no notion of talking of same time because simultaneity is something that depends on your reference frame. But the particle at a time t interacts with the field at the same time as this particle is at. It doesn't care what the other particle is doing. This particle, in this language, this particle never interacts with the other particle. It only interacts with the field. Okay. It has. So the retarded time has gone in. When you compute the electric field, it has kept track of the past history of the particle. But to evolve things forward, everything is local. Nothing now depends on anything retarded. The field here depends on what the field is doing at a different point. Remember, there are also some Maxwell's equations which you have to solve in with, apart from this. But those Maxwell's equations also never make reference to a retarded time. That's because the field at a point is influenced by what the particle at that point is doing. Okay. So there are also some Maxwell's equations you need to solve, right? You need to solve then some more equations. But this, huh? You need to know dynamics of the field also. That's right. So the field is also now a dynamical degree of freedom. But you see the field at a time t depends on the charge density at that time t, not on the charge density in retarded time. And the way we've got rid of the retardation is by making all the dynamics explicitly local. Okay. Do you see what's happening here? Now, if I draw the same diagram, what's happening is this is 1, this is 2, and then there's this field in the middle, right? I didn't draw it very well, but you see, and this field is sitting everywhere. And the particle here only talks to this field here at this time. And the particle here only talks to the field at this point in this instant in time. So now we don't have to keep track of the retarded dynamics for the field, but the field lives at every point in space. Okay. So we again have an infinite number of degrees of freedom. But no retarded times. Why is this more convenient for making a passage to quantum mechanics? It's because now we have the usual language of phase space. Right? In the Hamiltonian formalism, what we need is we need a phase space where you're given, in fact, it's a question that you asked, you're given initial data on one time slice, and now you need to evolve it forwards. This is that language. You're given the fields and the particles on one time slice, and you need to evolve it forward. But you don't need any past data. You just need data at one point of time, but you need data at every point in space also. Okay? In that language, we need to keep track of not data at one point of time, but of past histories. Here, you can keep track of data at one point of time. And that's convenient to make a passage to quantum mechanics. Is this point clear? This is actually quite an important point. And as I said, I don't know of any textbook which will emphasize this point.
Excuse me, sir?
Yeah.
Sir, I didn't understand this thing that the particle moves with respect to another particle, so it interacts via the retarded time, right?
That's right.
Now, when you introduce the concept of field,
yes,
it interacts with the field locally.
Yes.
So how can that particle interact with the other particle?
Because the field also interacts with the other particles.
But that in a different time, right?
No. So the field, this particle interacts with the field, and then the field interacts with itself. So eventually, by the time the field, so imagine, see what's happening. I mean, you already know this physics. You know what it's like saying, this particle sent a light ray that reached that particle, right? So what this particle did is it interacted with the field here, and this field eventually, this disturbance, propagated. It's like a wave. And imagine you have two boats in an ocean, right? You can write down some force law for the two boats just interacting with each other, right? You can say one boat interacts with the boat in some other way. And if you did that,
yeah, I got it.
It would depend on the retarded time. It would depend on the position of the boat, when the waves at some past time. Once you introduce the waves, then all the interaction is local. Right? So boat 1 creates some waves which go and reach boat 2 after some time, and then boat 2 gets affected. Okay, that's what happens here.
Got it. Thank you.
Okay, is this clear? This point? Because of what we just said. You see, the field and the particles interact with each other completely locally. So all we keep track of is what the field is doing at every point in space. And you see, when you keep track of two boats and you also keep track of the ocean, then you don't need to keep track of what was happening in the past. Then the boat interacts with the waves next to it, and each boat interacts with the waves next to it. Right? And so you don't need to keep track of so you never talk about boat 1 interacting with boat 2. You talk about boat 1 interacting instantaneously with the waves and boat 2 interacting instantaneously with the waves. And the waves also may be interacting with each other. But all that dynamics, you can just evolve forward in time. You don't need to keep track of past histories. Okay. But the key point here is that you do need to keep track of an infinite number of degrees of freedom. Why do you have to keep track of an infinite number of degrees of freedom? Because the field lives at every point in space. Right? The field is, you cannot get away by keeping track of a finite number of degrees of freedom. That's already clear. There's no magic. The magic is just that you're trading, instead of keeping track of past histories, you introduce a new degree of freedom, And you now define that on a spatial slice, and you keep track of that. Yeah. Okay. So this is why. So the point I want to make here is that relativity forces you to have to keep track of an infinite number of degrees of freedom. You can do it in two ways. You can do it either by keeping track of past histories and then working with these retarded differential equations or functional differential equations, or you can do that by keeping track of fields. Okay, and if you keep track of fields, then you have to keep track of fields at every point in space. Okay? In this course, we are going to take this approach, not that approach. And the reason we are going to take this approach is that we don't know how to do quantum mechanics with that approach. By the way, maybe there is a good way to do quantum mechanics with that approach, which hasn't been explored. But in this way, we can just do a straightforward passage to quantum mechanics. That's because this approach, fulfills the usual idea we have of how physics works, which is you are given initial data at one instant of time, and you can evolve it forward, and you can write down some Hamiltonian for it. Okay. Okay, is this point clear? No. Don't exist and so on are words we should be very careful of saying. What exists and what doesn't is a philosophical question. Who has a question? Yeah. So what exists and what doesn't exist is a philosophical question. Yeah. Does the wave function exist or does it not exist? So yeah.
The existence of field is introduced mostly as moving charges do not follow Newton's third law. So in order to explain that, we say
no. That's not why we introduce a field. We have to introduce a field for this reason, to make things consistent with relativity. If it was that you see, it's a more convenient way of keeping track of past histories. I don't know, more convenient, different way of keeping track of past histories. If it was only that they didn't obey third law, you'd say fine, they don't obey third law. So what? The third law is, we abandon it. We don't care about it so much, right? So if it was just the fact that things were not obeying the third law, we wouldn't care about it. However, fields are convenient because you see, what we say is when you send out some radio waves and some other particle picks it up, you can describe that interaction in terms of saying, well, you have a particle in the antenna which is interacting with the particle in the radio station in some far past that created the wave. But rather than that, what we say is, well, the particle in the antenna is responding to the radio wave at that point. So rather than talking about some past history, you just talk about some radio waves that fills everything. Okay? So it's another way of keeping track of these past histories. Okay? And now, okay, what exists and what are does the electron exist and so on. So these are philosophical questions. The field, we can say the field exists, right? But what exists and doesn't exist is really an ontological question. If you like, you can say the field exists, or you can say that it's only particles you observe and the field is a device. But this is not a it's not a very fruitful question. Or you can say only fields exist and particles don't exist. You can also say that. In fact, we'll kind of move towards that approach now. Yeah. That's right, exactly. Everything is local once you introduce the field. Exactly. Okay, good. But the important point I want to say here is why you have to have an infinite number of degrees of freedom. Okay. As I said, what is going, the thing we're going to spend, I'm spending a lot of time on this today, but everything we do in quantum field theory, all the complications, everything, this whole course is basically about doing quantum mechanics with infinite number of degrees of freedom. And so it makes sense to take a step back and ask, why did we have to do it? Why couldn't we have worked with a finite number of degrees of freedom? And you should realize it's because of relativity. Okay. Okay, now there's another reason, of course, which is the reason usually given in textbooks. And let me explain what that is. Okay. There's a second reason, of course, that it's useful to work with fields, which you would not see in that approach. It's also a physical reason. And it's the answer that some of you already gave earlier. Okay. The second reason is that, remember that let's say you had some particle, right? In quantum mechanics, when you usually do quantum mechanics, you say, well, you have some particle and you squeeze it to some position x. Yeah, okay. Now, when you squeeze it to some position x, okay, there's some uncertainty principle, and the uncertainty principle, tells you that delta p and delta x is of order 1. So if we make delta x very small, then delta p increases. And what eventually happens is that delta E, the uncertainty in energy, can become larger than the mass of the particle, the rest mass of the particle. By the way, whenever I write m here in this whole course, m here will always be what is called the rest mass of the particle. We'll often talk about particles and their masses and so on. And sometimes when you do courses on relativity, you talk about some relativistic mass. We are never going to use that. Okay, when we talk about mass, it's always this. We might want to talk about energy, okay, but mass is always just m, the rest mass. Okay? And if you do that, if you try to squeeze a particle in a very small region, then its uncertainty in energy increases, and therefore it's not clear if it's only that particle that remains, or if you have created additional particles. Okay, this allows for additional particles to be created. Okay, and this is another reason why we want to talk about fields. Okay? This is a slightly different reason from the reason we've been talking about here. Okay? And it's a reason that appears only in quantum mechanics. Okay? It's because in principle, once you try to squeeze particles to a small enough distance, there's some uncertainty in the momentum, which leads to some uncertainty in the energy. Okay? And that allows for additional particles to appear, which wasn't happening in classical dynamics. Okay? And what this is going to force us to do is it's going to force us to, in fact, maybe going back to the question that you asked, rather than talking about a fixed number of particles interacting through a field, which we can do in classical dynamics, we are going to have to talk about the particles themselves as excitations of a field. Okay. That's because that is a convenient language in which you can say we have one excitation, two excitations, or a number of excitations, rather than talking about the Hilbert space of a fixed number of particles. And I'll explain this in a second. Okay. So this is a kind of conceptually a slightly different reason why we have to have fields. The first reason was that fields were necessary to just describe interactions between two particles. But now we are saying, well, the number of particles itself might not be fixed, which we didn't see in the classical case. Okay, so we needed fields anyway to talk about interactions in some local way and go to quantum mechanics. But now we are saying, well, your number of particles might not be fixed, and so maybe it's just not convenient to speak in terms of a fixed number of particles with positions at some point. But rather, we should allow for number of particles themselves to fluctuate, and that in that the field is very useful in that it allows you to describe particles as excitations of a field and easily speak of variable number of particles. I want to do a short calculation right now to explain why this, the usual quantum mechanical notion of the Hilbert space of a single particle doesn't make sense, which we'll do in a minute. But this is, I just want to point out another reason why you might want to go to fields. Okay. Okay, good. Let me explain. Let me just do this. Yeah. Just one more point about this. One of I once heard a talk by Freeman Dyson in which he said this was the key point about field theory. And you could ask, what is it that field theory really teaches you about the world? Okay. So maybe it's convenient and so on. But you see, there's something that is kind of lost when you talk about particles, right? We talk about two electrons. Why do two electrons have to be identical? maybe they're kind of similar, but maybe one electron, some electrons are slightly more massive, maybe some are less massive, and so on. So when we just talk about a discrete number of particles, it's not quite clear why those particles have to be identical. However,
Excuse me. Yeah, so if two electrons did not have the same mass, we would not classify them as electron, right? So
yeah, you would not classify them as electron. That's true. But maybe there are particles which look very similar, but there's some variation, like 1% of variation in the mass, right? We have such classes. We talk about trees, right? Trees are not exactly identical, but we classify them as trees. So or maybe electrons are like footballs, right? So all footballs are not exactly the same, right? But we classify them as footballs. They're slightly different.
right.
They're tennis balls and so on, right? But you see, the point is electrons are not like that. They're really identical. It's not that there's some quality control which the universe creates and says they're identical up to 5% or 2%. Okay, they're really identical. Okay, and that is something that the field really tells you. Okay, so fields tell us when we do this fact that we just said here. Okay, fields tell us that all electrons are the same, are really the same. Not just the electrons, of course. Okay, I'm using electrons here as a phrase, but of course it tells us all Higgs bosons are the same, all photons are the same. Okay, all protons are the same, all muons are the same. Okay, so electrons is just one particle. It kind of tells us that all these elementary particles, which are excitations of the field, they're all really just excitations of the field, and there's really nothing to distinguish one electron from the other electron. Okay, and it's not It's not that we allowed some variance, but they're indistinguishable particles. Okay, and that's something that comes from thinking of particles not just as things which happen to be similar, but rather as things which are really excitations of a field. So really the underlying degree of freedom is there's some field, and these are really excitations of that. Okay? And that's why they're the same. Okay, this point will become clearer as we go along, but I just want to mention it. It's something else you should keep in mind. Okay, good. Again, something that's not always.
Excuse me, sir?
Yeah.
Sir, if the fields act as like some particles can pop out of the fields and then can go inside the field like that, then can we think of it like a infinite particle bath? The field as an infinite particle bath?
The field is not an infinite particle bath. The particle is an excitation of the field. Okay? So when we talk of the particle, I mean, this will become much more clear. Right now, we are kind of just saying some words. The particle will be an excitation of the field. Okay, so I don't know if you should think of the field as some infinite particle bath, but the particle will be some excitation of the field. Oh, is the AC on? We should switch it off because I opened the window, no? Sorry. Yeah. Huh? Yeah, but we don't want to cool the universe. Okay. Okay. Okay, good. So this is okay. Let me. We have half an hour more, right? Okay. So let's do a short calculation to explain first of all why this doesn't work. You could have said. By the way, I've said some words here. I said, well, you have delta E larger than m. This allows additional particles to be created and so on. But you could have said why. Maybe I'll write down dynamics where additional particles are not created, and that's just how it is. Right? Maybe I'll just impose by fiat that you have only 2 particles or 3 particles in the world. However, I want to now explain why this doesn't really make sense in relativity. And this is a calculation which good. This is a calculation which is done in standard QFT. You'll find it in many QFT textbooks. Okay. What I said so far is often not in textbooks, but what I'm about to say now is. You should still pay attention, but you can also look it up. Okay. So okay, great. So I want to explain to you why the usual position eigenstates Why doesn't make sense? Think of a single particle. I want to explain why it doesn't make sense to think of a single particle Hilbert space in relativity. Okay. So we're going to kind of do this by finding something which doesn't make sense. Okay. So we'll do this by contradiction. Let's say it made sense to think of physics of single particle. In fact, this will be the physics that we were discussing earlier. It's a free particle. Okay. So we don't even need to, we talked about dynamics and so on, but let's just talk about a free particle. Okay. So then we could say, so I don't know, we'll find an absurd conclusion. Okay. So assume this made sense. Then we can talk of a single particle state, which is X, okay, which is a particle at position X. Okay, this is what we usually do in quantum mechanics, right? This is how we taught quantum mechanics, which is, you have some particles, and this means it's an eigenstate. You can give some wave function, you can kind of spread it out, but this is a particle at position X. Okay, this is a delta function normalized state, so it's not really normalizable. But what I'm about to say doesn't matter in that. It doesn't matter. You're free to smear this out a little bit, make it normalizable. You'll find the same conclusion. Okay. Okay. So what we want to check now is in time t, it should not propagate outside the light cone. This is a basic consistency check with relativity, right? If the particle is at some position here, it shouldn't be outside the light cone in some time t. What we want to compute, what happens to a state after time t? It evolves, right? Okay. So after time t, the state becomes this. We want to check if it can be measured outside the light cone. For that, we want to determine this matrix element. If you know what this matrix element is for different values of x prime, we can check if this vanishes. Okay. So this should vanish Is this fine? What happened to Zoom? Went off? Came back. Yeah. This is a basic consistency check with special relativity. Is it clear? Okay. Now we have to guess, we have to determine what the Hamiltonian is. So what's the Hamiltonian for this particle? Is what? P squared plus m squared. You mean the square root of that? Good. Okay. Yeah. Good. So the usual for a free particle, usually, we might take a Hamiltonian which is just p squared. But then you might say, well, if you took that kind of a Hamiltonian, then you shouldn't be surprised that you found a contradiction with relativity. So we'll take a Hamiltonian that's in fact consistent with special relativity. In fact, it has to be that, because we know that single particle in the end has a classical Hamiltonian, which is given by square root of p squared plus m squared. And so let's work with this Hamiltonian also in quantum mechanics. And with this Hamiltonian, we expect that the particle shouldn't propagate outside the light cone. Okay. Okay. Good. So now let's evaluate that. How do we evaluate that? Well, we introduce a complete set of momentum eigenstates. Here you should be on the lookout for the 2 equal to 1 units. Okay. So you should catch anything that happens here. Okay. Okay. So let's introduce this is a complete set of eigenstates. This is that matrix element. This is what we're trying to calculate. Yeah. So this is now just e to the minus I square root of p squared plus m squared t e to the I t dot x minus x prime. Is this fine? Okay, let's call this quantity G. Yeah. Okay. So we have to evaluate what this integral is. This is the kind of integral you'll often find, and the way you evaluate it is basically by going to the right coordinate system. Okay. So you go to some coordinate system. You have some x minus x prime. Okay, and you call it mod r. Okay. And then what you'll find is that this looks like T I
Your voice is not audible.
So you're not audible, sir.
hello. Can you hear now in Zoom?
Yes, sir.
Yes.
Okay. Okay. So let's go for some time. Hopefully it works. Yeah. Okay. So we want to do this calculation, and I said there was a 2 pi angle which didn't matter, and so that's why this became 2 pi squared. Yeah. Okay. And this is just d of cos theta, sine theta, d theta. Okay. Good. So when you do this integral just becomes IPR minus e to the minus IPR. Okay. And we have a p squared dp, and that becomes p dp, and we get an IR. Yeah. And I've just done the integral over cos theta. Okay. And this just becomes 2 by r integral e to the minus I square root of p squared plus m squared into t into sine PR into p dp by 2 pi squared. Yeah. Okay, is that good? Please check this. I'll also try and check. But sometimes.
Yes, sir.
Yeah, okay, good. Now this integral we can actually do exactly. It's one of those things you have to look up some old Russian books for, but you can do it if you do that. I'll tell you what the answer is. Okay. So this integral you just do using this formula. X e
Excuse me, sir. You are not audible again, sir.
How long will this last for? Okay. So this is the answer. Okay. And now we want to consider the situation we are interested in is the situation when r is, let's just consider a limit. We want to see if this vanishes for r larger than t. In fact, it's pretty clear it doesn't. Right? It's just some Bessel function. You take r larger than
What is K2?
K2 is a modified Bessel function, second, order 2.
Oh, yeah.
Yeah. So, if you just take r larger than t, it's some number. It clearly is not vanishing for, far larger than t. In fact, it doesn't vanish anywhere. Doesn't vanish even for very large r. Okay? So consider. By the way, we are already in trouble if it doesn't vanish, slightly outside the light cone. You should realize there's no such thing as having slight violations of relativity. Okay. If you have slight violations of relativity, then you can violate relativity by a big amount. Okay? So either things are consistent with relativity or things are not consistent with relativity. Okay. So the fact that it doesn't vanish, does not vanish. And that's just obvious, right? There's just some number. So it's some second Bessel, Bessel function which we have studied, and that's not zero for all positive numbers. Yeah. So it just doesn't vanish for r larger than t. So it's not. So this, if you think of this state x as some particle at a single position x, and you try to do this evolution, it clearly is not consistent with relativity. In that, with this Hamiltonian, things propagate outside the light cone. In fact, the point here is they propagate arbitrarily far outside the light cone, and you can check that, e to m lambda goes like e to the minus m lambda for m lambda much larger than 1. Okay. So even in this regime, k2 of m square root r square minus t squared goes like e to the minus mr. Okay. Far larger than t and mr larger than 1. Okay. So in the case where r is much larger than p, and where it's also much larger in the scale set by the mass. Okay. Notice, by the way, that the mass here in the units we are working in, which is h bar and c is 1, also sets an inverse distance scale. You can check that. And so e to the minus mr in the limit where this is much larger than 1. This is just, sorry, in the units where, in the limit where r is much larger than 1 over n, this goes like e to the minus mr. So it's decaying exponentially, but in fact, it's not vanishing anywhere outside the light cone. Okay. So what this is telling us is that, you start this particle, and if you really want to think of this state as, some state at position x at a time t, then you're in trouble because this Hamiltonian instantaneously evolves you everywhere outside the light cone. It just gives the particle some amplitude to be everywhere. And that's clearly inconsistent with relativity. Okay. And that's why, you, even letting aside the issue of dynamics, even with free particles, you would not be able to construct a theory of free particles consistent with relativity if you just restricted yourself to a fixed number of particles. Okay. Okay, good. Let me now say just a few general words about how fields help, and then from the next lecture, we'll start discussing in more detail how, maybe I can go to the next slide. Yeah. Yeah. Something, yeah.
There are some subtleties regarding orange gradients and divide by square root of omega.
What subtleties? Regarding subtleties where? In what we have done so far?
No, in the we are doing in measure of the integral.
Which integral here was there subtlety with? This measure. No, this measure there's no subtlety. Remember, we just introduced a complete set of momentum eigenstates. We're just doing ordinary quantum mechanics here, as we were taught in our BSc courses. So D4P. No, there's no. Good. But there's no scope for doing any of that here. There's no scope for doing any of that here because what we have here is just ordinary quantum mechanics. We have a Hilbert space of particles at position x. Apart from the operator x, we have another operator p, and p has some commutation relations with x, okay, which is that xp is equal to I. When you do that, you will see that the eigenstates of p are e to the ipx, and then the completeness relation is just forced on you. It's just the Fourier transformation here. Okay? So you'll get some completeness relation if you normalize the states x to be delta function states. You'll get this completeness relation. So it's not like you're allowed by hand to insert something else. There's a completeness relation, which is 1 is equal to integral pp d3p by 2 pi cubed. There's a convention which we used here, which is 2 pi cubed, that you could change by normalizing the state differently. It's not like you can just put some omega or something there. So, within the framework of quantum mechanics, we don't have any freedom here to do anything. This is how we do things, right? So you'll have to change the idea of thinking of a single particle and its Hilbert space consistent with relativity. Is that clear, or are there any other questions about this? Okay. I really want to encourage you to ask questions, because if you don't ask questions, I won't know if I'm communicating or not. Okay. So please do ask questions, so I will know at least it's making sense.
This still holds like a fixed number of particles.
Right now, we're just talking about one particle.
But if there are more than one particle, the particle
Yeah.
number is fixed.
But you see, if you want to talk of quantum mechanics in terms of this particle Hilbert space, you first need to make sense of one particle. By the way, it doesn't matter if you took like 3 particles, and even if they were all free particles, this calculation would just be the cubed of this calculation for that situation would just be doing this calculation 3 times. Okay. So here we are just talking about free particles, and the point is that this single particle Hilbert space, where you think of particles at a given position, is just not going to make sense. Okay.
Excuse me, sir.
Yeah.
What is the physical significance of this GXS prime?
This gx prime was telling us whether our system is consistent with relativity or not. This is gx prime here. It's defined here.
Yes. So x prime e to the power minus iht x, right?
Yeah.
So does it? I mean, in the Heisenberg picture, it is defined in that way, or is it like pure quantum mechanics?
It's a number. It's not. There's no Heisenberg or Schrodinger picture here. This is a C number function.
Oh, okay. Yeah.
It's not. It's not an operator. It's a matrix element of some operator.
Hmm.
So there's no. Doesn't matter what picture you use. It's a number you're calculating. It's a matrix element. Okay. So how do fields help? Okay. So in fields, as I said, we'll drop the idea of these particles X. So in fields, with fields, particles will be excitations of the field. And the fundamental degree of freedom will be some field phi. Will be some phi of x. Okay. Let me write it as a function of t and x. Okay. And in fact, the uncertainty principle that we find will now be some uncertainty between phi and phi dot. Okay. Some uncertainty principle and we'll make that more precise next time. Okay. So we will no longer talk of this single particle Hilbert space or these position eigenstates X. Rather, our Hilbert space will be, our degrees of freedom will be this field phi, okay, and the uncertainty principle will be in terms of phi and phi dot, and the Hilbert space we'll construct will be for excitations of this field phi. Within that, we will still be able to make sense of some single particle states or two particle states and so on, in the limit where we separate these particles very far. So we'll be able to say, well, there's one excitation of this field, or there are two excitations of this field. Okay, but we'll never talk of these kinds of single particle Hilbert spaces. Okay, now that doesn't mean we can't speak of localized excitations. And I'll say this again, even in field theory, we can speak of localized excitations. Okay, and this is important. And we'll get back to this like maybe in 3-4 lectures from now, after we've developed some of the formalism of field theory. So it's important that what we said so far is not a statement that there is no such thing as a local excitation. Of course, there are things such as local excitation. So we can think of an excitation, some state like this, which has an excitation here. I'm just drawing a picture, okay? Just like you think of waves, you can say there's a wave here, and everywhere else is a vacuum. And here it looks like the vacuum. And then what does relativity tell you? Relativity tells you that the boundary of this excitation doesn't propagate any faster than the speed of light. Okay. Okay, faster than c. And so if you look at it after some time t, maybe the excitation has grown, but it will strictly obey the rules that it doesn't grow faster than the speed of light. Okay. Okay. But this excitation, when we think of such local excitations, which are localized in some region, it will turn out that they will never be single particle excitations. Okay. So local excitations are never single particle excitations. Okay. So when we think of local excitations of this kind, where you have some excitation in some bounded region, we will see in a few lectures from now that they're never single particle excitations. They always have some uncertainty in particle number. Okay, and then there is indeed a principle that tells you that they don't grow faster than the speed of light. And this right now I cannot demonstrate, but we'll come back to it in a few lectures from now once we've set up the basic formalism of field theory, and then we'll check this. Okay, so just remember this calculation that we did, and then we'll go back and see how in field theory you can think of local excitations and how they are consistent with the principle of relativity, but they're not single particle states. Okay, good. So this is all I wanted to say for today. Basically some general overview, and let me just recap. Okay, what we've discussed. We've discussed why it is that fields need an infinite number of degrees of freedom. Okay? There are two ways, of course, to do that in classical dynamics. But then we said, well, we look at fields because it's more convenient to go to quantum mechanics by looking at fields rather than looking at retarded positions. And then we pointed out how quantum mechanics of single particles doesn't make sense in relativity, because it allows, if you try to write down the natural relativistic Hamiltonian, it allows particles to propagate outside the light cone. And then I've indicated how fields will help us in that. But from next time, we'll start setting up the formalism of field theory. Yeah. Okay, are there any questions about this?
So what do you do if we really want one single particle?
We can have single particles, but they're not localized. Or you can have localized excitations, but they're not single particles. Yeah. Okay, good. So we'll meet on Wednesday, 11:30. See you.